Everybody to the colloquium. And today we have Conny Aerts. Dr. Aerts is from Belgium. She's in charge of a subgroup that is a subgroup of the Kepler science team, has an associated group called CASC, and CASC is folks that study asteroseismology. And Conny is in charge of about 20 people that are studying asteroseismology in eclipsing binary systems. And I think you'll find asteroseismology to be fascinating. I won't talk any more about it, but here she is. Thank you for giving the colloquium.
Thank you. Thanks a lot. It's great to be here after some fighting against the snow. But anyway, that's life. And so I'll be talking to you today on my pet topic, which is asteroseismology, which stands for the seismology of stars. And we're having great fun these years and many more years to come, because we have 2 operational space missions delivering magnificent data for us. And we have been preparing that for more than a decade. So finally, when the data are there, it's really great. Why do we want to bother? Well, our main goal here, and I'm showing you here an HR diagram, effective temperature luminosity, where you see all the stars, so to speak, indicated in various ellipses here. What we want to do is improve our knowledge of stellar evolution. That's my goal. I'm not a planet hunter per se, but if you want to know how planets get born and evolve, you better understand how their parent stars behave, evolve, because this is, of course, tightly connected. So what we want to do is understand the stars better to help the planet community. And I'm giving this example of one planet to show you that we sometimes understand very little about stellar evolution. This is a cartoon of a planet discovered around a compact star, compact hot blue star, which is here in the HR diagram. And this planet was found thanks to asteroseismology, because this star, this parent star, is having multiple oscillations. And so in order to find that planet, you first have to understand the oscillations and get rid of them, to put it in a negative way, so that you can find the planet by the timing method that is imposed by the planetary motion on the oscillations. This was discovered recently and was published in a paper in Nature. Now, this planet shouldn't be there if we take our normal stellar evolution theory, because stars go up the giant branch, and then some of them seem to lose their hydrogen envelope and become compact blue stars. But how can a planet survive this? It's not supposed to be possible unless it was formed in situ after the envelope was thrown away. We have no clue how that happens. So this is just one example of our lack of stellar evolution knowledge and the coupling to planetary research. And I'm sure there are many, many more things that we don't know. Me, as an astroseismologist, this is my hobby. Very high mass, high luminous stars, because there we understand very little of their evolution, while they are the ones that are important for chemical enrichment and so on, because they will explode as supernova, and we know more or less how that happens, but not in terms of the internal physics. So, well, I'm coming from here and I'm moving down in mass just to go to cooler stars like the Sun that have planets. For those of you unfamiliar with asteroseismology and stellar oscillations, here is an HR diagram again, just an example. Here is the Sun. Here is the red giant track where the Sun will be in its future life. And as I said, some stars lose their hydrogen envelope and then become compact stars. And what happens next, we don't know very well. And how this takes place, we don't know. So let's look at individual stars. One that's here, one that's here and one that's there. They are not connected, but just to see how they oscillate. And when we study oscillations, we go to the Fourier space. So we measure a time series, either in luminosity changes in time, or spectroscopy, radio velocity changes. And then you make a Fourier transform and you find a periodogram, as we call it. So here is frequency, here is power in units, depending on if you have brightness or velocity measurements. This is the sun. We understand very well how the sun behaves. And you see the beautiful oscillation signature in this plot from the BISON network. That's the Birmingham Solar Oscillation Network. You see here an excessive power that peaks around 3 millihertz. So that's 5 minutes if you put it in the time domain. So the sun has really numerous oscillations. Each of these peaks is one of them. And it is centered around periodicities of 5 minutes. The oscillations are caused by the convective motions in the outer layers of the sun. Okay. Now let's move up and let's take a red giant star. What I'm showing here is pre-Kuro, pre-Kepler, just to show you where we were before these missions. This is the first firm detection of oscillations in a red giant star. It was done in 2002 with a small telescope. We do not necessarily need big telescopes for this work. No, we need telescopes during a long time. So this is time domain astrophysics. And you see here, well, compare the noise level, that's one thing. This is an amplitude diagram in meters per second. You see an excess power here. Look at the frequency range compared to this one. Much lower frequencies. Why? The star is much, much bigger. This is a red giant. This is I compare that with musical instrument. This is a bass, right? While the sun is just a normal instrument, let's say. So much longer periods, because these oscillations are in fact sound waves, and they have to travel through the star. So traveling through the sun takes much shorter than traveling through this huge red giant, right? So the frequency is in a much lower frequency regime. This is much harder to measure for the observers because we need a longer time base. Anyway, here you see a frequency excess power. Not clear where the noise level is, I would say, if you are first confronted with this. So you have to learn to understand how to get these signals and make sure that you're not measuring noise peaks, because you don't want to model them as a seismologist. Okay? So then we go here, a compact star, another frequency spectrum here, frequency in millihertz. This is a very faint star, so we can't do it in spectroscopy in this case. This is brightness variations. And here you see a clear noise level. These are data taken with a 4-meter telescope in La Palma with an ultra-fast photometric camera. And you see here an excess power near 7 millihertz. It's a much more compact star than the sun, yet it's not too different in frequency. Why? Because this star happens to be a helium star. When a star is here, it has lost its hydrogen, so the chemical composition is different, and that implies that if your material is different, your oscillation signature also changes. Okay? So that's just to show you that various types of stars across this diagram have various types of oscillation signature in the Fourier domain, but we basically understand that. It's following our theory. So why is asteroseismology useful? Well, because it can help. And so the word is composed of 3 Greek parts. We want to do a reasoning, or a discours, as the French can pronounce it so nicely, using the oscillations to get information on the interior stellar structure. Okay? How does that work? Why is it possible? Well, with classical observations, you can't derive information on the interior of a star. You can measure its basic temperature, you can measure its basic gravity, but that's about it. So your whole evolution theory you can confront with only a few numbers that are deduced from the outside of the star. Right? Now, if you have oscillations, you can sort of see them as ray paths, and here there is a drawing of a few of these oscillations. These are acoustic waves, in fact, and you have the red one is an oscillation, the yellow one is another one, the green one is another mode, and this purple one is another one. And what do I want to have as a seismologist? I like the purple one, because it probes the core of the star, and the life of the star is directed by the core. You know, what is happening there is determining how it will live on. Unfortunately, these are hard to measure. The red ones are easy to measure. The spectrum you saw from the sun is basically was a representation of these red types of oscillation. I don't know if you can see, it's not so clear on the screen, but there's a dotted line here encapsulating where these rays propagate, here in yellow, here in green. So what do we want to do as seismologists? Let's assume that we can measure this yellow oscillation by surface effects, either in velocity or in brightness. And let's assume we can also do that for the green one. The green one probes a tiny little area different from the yellow one, and this is represented here by repeating this drawing many times. So if we can measure a yellow oscillation and a green oscillation, the frequency difference of these two allows us to probe the physics of what is only green here and not yellow. That's what we want to do, okay? So what do I need as a seismologist? I need a lot of modes, preferably more than the two here, because these two only allow me to probe one layer, and I want to do this layer by layer across the whole star. I want close frequencies, and I want to measure their frequency value very accurately. And I need to understand the type of mode, and then I can do my work, okay? This may sound simple, but it's not, because you need high time resolved measurements during a long time of tiny little effects. So that's where space helps us. What do we want to achieve with that? Well, in general, you see, what are the unknowns in stellar evolution in the models that we have? There are various phenomena that we do not know how to deal with, and I've listed them here. An important one is convective overshoot. So different stars, as in this cartoon here, have different convective layers, which are indicated by the orange parts here. But we don't really know where this, radiative goes to convective, where the change is. For the sun, this is not so important. Frankly, the sun for me is just a boring, simple star. Okay. For a massive star like that one, it's very important, because the change here across this area from convective motion to radiative motion determines how much material takes part in the nuclear fusion. Everything in this orange part is taking part in the nuclear fusion, so it's directing the life of the star. And if this were to be situated tiny little bit further or less far, then the evolution changes quite dramatically in terms of age. And so we want to position this layer. And we can do that from seismology. That's just in exactly the same way like Earth seismologists determine the extent of the iron core of the Earth by using seismic waves, rather than drilling a hole here until we arrive at the iron core. We can't do that. So we use exactly the same techniques as the geophysicists. And then, of course, there are stars like this one that are intermediate, typically between 1 and 2 solar masses, that have both an outer convective layer and a central convective core. And so, bubbles here that have convective motion have inertia, so they overshoot this radiative layer. We don't know how much. We think it must take place. It's logical, but we can't characterize that very from first principles. So we use an unknown parameter in our stellar evolution computations, and we want to tune that parameter from the seismic waves that pass through these layers. Okay. Another thing that we know very poorly is internal rotation. We know that the sun is not a rigid rotator because it has these seismic waves, and we can use that information to probe the interior rotation. Again, for the sun, this is not so important for her life. It is very important again for these massive stars, because rotational mixing again determines how much material can take place in the nuclear fusion, and so we want to have information on the internal rotation of a star. You cannot do this from measuring the surface rotation. That's clear. So oscillations will help us. Then there are a number of physical phenomena that we know how to deal with, we think, but they haven't been tested observationally. That's what we want to do. And one thing that is, well, if you ask me what the most important byproduct is of an astroseismologist's analysis of a star, it's the stellar age. This is something that is really difficult to determine, and I'll show you how we can do that. Let's go back. I have understood that not all of you are astroseismologists. So here is a very simple cartoon of how to describe an oscillation, which you've probably all had. In a one-dimensional body, how do you describe an oscillation? Well, you have a frequency of the oscillation, or the period, if you like. That's one number. And you have the number of nodes. 1 here, 2 here, 3 here, and so on. None here, that's the fundamental. If you like to couple that to musical instruments, it's exactly the same, right? So, fundamental, first overtone or first harmonic, depending on your terminology, second harmonic, and so on. And then you have the amplitude, yeah? The amount of deviation from the equilibrium. So, for a one-dimensional body, for each oscillation mode, you need 3 numbers: the frequency, the amplitude, which are real numbers, and the number of nodes, which is a natural number. Okay. Now we go to stars. These are just 3-dimensional musical instruments, if you like. Yeah, you have a question?
Yes, excuse me. Are you plotting density or displacement? I mean, these could be acoustical waves that are where the density is perturbed, or displacement of material.
Yeah, we use both. And also the temperature, the pressure, each of them have their eigenfunction, as we call it. And all of those have these 3 numbers in the 1D case. Okay?
And what about magnetic fields? Do you probe magnetic fields?
Oh, let me come back to that later. Let's start simple first, okay? So here's a 3D oscillator, types of modes. Now we need, in addition to these 3 numbers, we need 2 more. Why? Because we have 2 dimensions more. It's very simple, okay? So we still need a frequency, we still need an amplitude, but rather than giving one value for the nodes, we need 3 values. The number of nodal surfaces inside the star and the number of nodal lines on the star. So here you see what we call Doppler maps, right? So this is an image of a star where the symmetry axis is pointed here. That's usually the rotation axis, but it could be a magnetic axis if the star has a strong magnetic field. These white areas are lines where the elements do not move during the oscillation. Red is coming towards the, well, blue is coming towards you, gives a blue shift in the spectrum. That's why I color-coded it blue. And the red parts are moving towards the interior. Here you see it in a movie. So what do we need to do our seismology? We need to determine the frequency, the amplitude, and 3 numbers, of which 2 are the, what is usually called the L and M, the degree of the mode L, which is the number of nodal lines on the surface. This is 1, 2, 3 for all these 3 stars. And M gives you the azimuthal order, as we call it. That's the number of nodal lines passing through the symmetry axis. So it's 0 here. That's what we call a zonal or an axisymmetric mode. It's 2 here, 1, 2, and it's 3 here. Okay? So these are just numbers that characterize the modes that we need to confront them with the theory. Yeah? How to do this observationally is very difficult. Ideally, we would want to have a high-resolution spectrograph available for us on a big telescope in a network around the globe so that we can observe continuously. And then we could do what we call Doppler mapping. Yeah. So here are all non-radial pulsators, and this is a blow-up of one spectral line. This is a simulation, of course, not real stars. This is a changing of the spectral lines according to the oscillation, as you see. And the line that doesn't move here is just a fixed spectral line that the star would have if it would not oscillate. Okay? So by studying this, and we can do that from the ground since many years, you can see, without being an expert, that these line profile variations, as we call them, are connected with the type of mode. So if we could measure this, we have tools to reconstruct how the oscillations take place. If you want to learn about that. This is a whole lecture by itself, even many more, but we can do that. The problem is that we can't get these observations. We can get them, but we can only get them during a short amount of time, because you need a large telescope to do that. You need a high-resolution spectrograph, and you need it for a long time to unravel the mode beating that happens in a star. So while we do have such studies, and while real stars do that, and I'm showing you here a real star that behaves like that, just to show you that this would in principle be possible, the interruption in the data is killing us, which is a pity. So how can we get non-interrupted data? We have to go to space, because even the best organized networks of telescopes from the ground, they typically give me a duty cycle of 50%. If the weather is fine, no instrumental problems, etc. And this is insufficient, okay? For spectroscopy like this one, we can't even get there because we simply don't have that many spectrographs. But, you know, it would be really fun if we could have this from the ground. We cannot do high-resolution spectroscopy from space yet, so this type of information is unfortunately very scarce. We do manage to move from kilometers per second to meters per second these days, because we can see the oscillations at a much higher precision, thanks to the planet hunting people who make these very stable spectrographs, and then we use them for our oscillations. Okay? So, how does it work? Let's go to the sun this time, a SOHO image, a SOMO spectrum, frequency, power, and you see the very nice signal. And you need not be an expert to see regularity here. So this is a blow up here of this central area. And you see that there are patterns in this oscillation spectrum of the sun. One pattern is the difference between radial modes of radial order 20 and 21. What does that mean? A radial mode is just up and down. Sun does that, okay? And so the number labeled here is the number of nodal surfaces inside the sun. So these are the eigen surfaces where the oscillation does not move, okay? That's just like the guitar I just showed you. Yeah. For the sun, we can unravel that beautifully, and we have this, what we call the large spacing. Now you can do the mathematics, I'm not going to show that here, but the large spacing in a frequency spectrum of a pulsator is directly connected with the sound speed inside the star. And of course, if you have a core boundary, and you have a distinction between convective motions and the radiative envelope, there is a discontinuity at this core, and depending on where this continuity is, your sound speed changes. But what's even more important is that your sound speed gradient changes drastically there. And this gives you a signature in your oscillation spectrum. And this signature is what we call the small spacing. That's the difference between modes indicated here, L equal 1, L equal 3, and the number of nodal lines differs by 1. So again, you can do the mathematics for that, but we can use this small spacing to derive the extent of the core. Now let's say we do that for a star like the sun. That's very interesting, because the sun doesn't have a convective core. I just said that it was a bit boring, but it is building up gradually its helium core, very gradually. So the position of this boundary is telling you directly how old the sun is. All you have to do, well, sounds simple, is measure two numbers, the large spacing and the small spacing, and you have the age. And for the sun we can do that with a very high precision, and then we place the sun, let me skip this, in this diagram, which is called the asteroseismic HR diagram. So what do I plot here? This is the large spacing in microhertz, this is the small spacing, and the blue lines here indicate where the sun is, just by measuring these two quantities from the Fourier spectrum and averaging them out. Okay? We have a high precision measurement. The error bar is smaller than the width of the lines here. What else can you see in this diagram? This is an Hertzsprung-Russell diagram, so it's an evolutionary diagram. Here is the ZAMS, zero-age main sequence. This is where stars are born, between 0.7 and 2 solar masses in this case. And how do they evolve? Along this line, as their central hydrogen fraction decreases due to the burning. Hydrogen is transferred into helium. And so let's see where the sun is. Well, the sun is on the 1.0 mass track, luckily. Okay? And it's there about halfway its main sequence life. We know that. Yeah. We know the age of the sun by various means, independently from seismology, for instance, from meteorites and so on. So we can calibrate the age potential of seismology by comparing these numbers. And it turns out that for the sun, we have an age calibrator with a relative precision of 0.1%. Of course, we want to do that for stars with exoplanets, because then we can find out how the formation and evolution of exoplanets behaves, okay? So it works for the sun perfectly well. Does it work for other stars? Yes, but let's first go to the rotation of the sun, and then we can see where we can get for other stars, okay? This is an inversion of the rotation of the sun from helioseismology. So what we do here, well, you know that if I were to play guitar here, you could map all the sound frequencies, right? If I'm at a podium that starts turning now, it sounds very differently, okay? That's the Doppler effect. Your frequencies are changed due to rotation, okay? The way this is done is written in this formula. Again, I will not give the derivation, but the frequency that you measure as an observer is on the left-hand side, is the frequency that I would have caused if I were not rotating with respect to you. And that is shifted by a certain amount where the m value, which is the number of nodal lines through the symmetry axis that I talked about before, times an integral over the body where the internal rotation rate is multiplied by a function that's dependent on the eigenmode. Okay, we know that function from the stellar structure. So let's assume that we can measure a lot of frequencies, really a lot of them. I mean tens, even hundreds. Let's assume we have a good model, which for the sun we had. I just showed you that in the seismic diagram. Then we can predict this value. I bring it over there. Let's assume we can do mode identification. So we have the m value. I bring it over there, and I invert these two integrals. That leads me to a direct measure of the internal rotation frequency of the sun. And that's what you see here in a color-coded diagram. Okay? So what is at once visible, this is the color coding, is that at the equator and at the pole, the sun does not have the same rotation frequency. You know that. It's different. The sun has differential rotation. You can also see that the color, sometimes I give this to kids, and they are very good in doing helioseismology, because then I take away this black line here, and the task that they get is, draw me a line where there seems to be a change in behavior. And all these kids, 4 years old, they draw this line at the right place, at the tachocline of the sun. It's remarkable. You see at once what is happening there. And this is the position where this boundary is between the convective outer zone and the radiative zone. Again, for the sun, it's not so important for its life, but it is important for its magnetic field behavior. So there is an effect. Okay. So the sun has non-differential rotation in its exterior, and is getting more and more homogeneous, let's say, as a rotation frequency as we go deeper to the interior of the sun. The question is, how does that couple to the magnetic field of the sun, and what do other stars do? So we want to understand how this works. It works for the sun. Let's go to another star. And this is the first, I would say, successful case. A copy of the sun, Alpha Cen, which is a binary with a K companion, long term. This is spectroscopy, and here you see the frequency spectrum in a power diagram obtained by a B-side campaign. So here they have tried to avoid the daily rhythm in the data by continuous observations. UVES is a spectrograph mounted on the 8-meter VLT in the Atacama Desert of the European Southern Observatory. UCLAS is a spectrograph in Australia. So these two sites have been measuring Alpha Cen, which is a star which is very bright. just as a test case to see what we can do from the ground. You can see this beautiful oscillation spectrum, very similar to the one of the sun, as should be, because this has the same spectral type. A spectral type is information based on classical spectroscopy. But then, if you look in detail, well, this peaks here where, near, let's say, 2,400 microhertz, it is not a copy of the sun. This cannot be correct, because the sun peaks at 3,000. Okay, here's the peak of the sun. So by doing seismology, you go really 1 order of magnitude better than classical measurements. Okay. Now you can derive all the frequency peaks, beautiful low noise level here, and then you can see that 42 frequencies are significant, as we call it. The mass of this star is 1.1, so it's just between these 1 and 2 zero mass stars where you start having a convective core, but it doesn't have one yet because the seismology would tell us. The age can be probed with a better than 10% measure from this seismic HR diagram, but we are not getting enough frequencies from the ground to do an inversion of the internal frequency of the rotation. This is a pity. We are trying, but we have too few frequencies. Yeah. So that's why we need to go to space. I'm not going into further details. Just showing you an HR diagram again, temperature, luminosity. All these dots here are stars for which we had a detection of solar-like oscillations before the Kuro mission was launched. Now there are many stars, meanwhile, given that Alpha Centauri was the first one, and that was 2001. So we're in a very young research field here. But for all of them, well, we can do the large spacing, and the large spacing gives you the sound speed, as I said. For most of them, we can estimate the small spacing, which is a measure, gives you a measure of the age, but not very accurately like for the sun, but still. For none of them, we have the internal rotation, except for the sun, okay? So what we need from a seismic point of view, I'm not a planet hunter now, is to do a few of these stars, but with much higher precision in the frequencies. So we need long-term monitoring. The discovery monitoring campaigns here, they can be typically 2 weeks, that's fine. But to go deeper and to do better, you then have to go to several months, okay? And that's where we are heading for. This is as far as I'm aware, the best multi-site spectroscopy campaign of the Solarlike oscillator. This is for ProSian, an F-star evolved, of which we knew there were oscillations ongoing. This is a campaign set up in 2007. 11 sites at 8 observatories cover 26 days. This is an immense effort. You have to imagine that this is typically between 50 and 100 astronomers being, active during 1 month. It's still much cheaper than a space mission if you go to the funding, but you don't get very far, compared to the discovery work. You can see beautiful oscillations, and different colors are different spectrograph at different observatories, so very consistent. This is meters per second, so it's beautiful, but yet we have a limited number of modes, typically a few of tens, right? We cannot do internal rotation, and for this star the modeling is very difficult because it has a condensed core, it's slightly evolved. So we can understand this much better if we were to have data for hundreds of these stars, because then we can treat them as a group and we can do ensemble asteroseismology. So that's where the space missions come in, and I cannot resist to show you this diagram because I'm a spectroscopist and it's really giving me much more information if I could have spectroscopy. We can't do that from space, unfortunately. This is telling you why I want that. This is the sun again, frequency, power, and the red part is the spectroscopy experiment, the blue one, a photometry experiment, and you can see why the spectroscopy would be better, because the oscillation signature of the sun, which you see here, is much better in signal to noise in spectroscopy compared to photometry. It's still beautiful in photometry, but you can gain a lot from spectroscopy, and that's why ground-based efforts are still worthwhile. specifically for very bright stars, because Kepler cannot do first magnitude stars. I mean, it's just impossible, right? So anything with a magnitude below 6, both for Kuro and Kepler, is too bright. So for them, we still have to rely on spectroscopy. MOST can do that, and it has done so for various stars, but MOST has the limitation that it can only look for 1 month, typically, a bit longer maybe, to stars. And that is simply short for a seismologist. It's too short. The frequencies are, the precision of the frequency goes as 1 over the total time base. And then 1 month is very, very short for me. This is an overview of Kuro. Kuro, yes, maybe I should have said that here, because that's so obvious to me, but not you probably. The Kuro mission, this stands for Convection and Rotation of Stars. Originally, it didn't get funded. Then they changed it to Convection, Rotation, and Planetary Transits of Stars. And then it got funded, okay? That's just the fact of life. We don't care. They can have the planets. We can do the seismology, okay? That's the deal. Kuro works differently than Kepler. This is the first image of Kepler that was on the website, in the sense that it has a seismology program where 10 stars, very bright stars, are observed with a cadence of 32 seconds, so very high. And then faint stars, 12,000 per CCD, are observed with a cadence of 512 seconds. So compared to Kepler, that's still very frequent. Huh? Kepler, in its long cadence, has integration times of ½ an hour. In its short cadence, of 1 minute. Okay. So Kuro was launched in 2006, December. It was commissioned, and last year we had a symposium on the first, public presentation of the results. Here you see again an HR diagram, this time in color. And by that time it had in its I'm a seismologist, so I'm reporting on the seismology right now. Okay. It had measured these types of stars. So you see along the main sequence from solar type stars up to very high masses and along the giant branch. Okay. So all these results are available now, at least to us. I'm highlighting just a few. For the solar-like oscillations, which interests the planet people most, of course, Kuro found for the, I say the first time, solar-like oscillations in F stars. You see 3 of them here. You have a power excess very clearly in this star. This is 6th magnitude. We go up to 7th and we go up to 8th, and then it becomes difficult. The Kuro mission has a tiny telescope compared to Kepler. And if I compare the noise levels in the Kepler data and in the Kuro data, then it scales exactly according to the telescope size. So that's normal, okay? The only thing is that Kuro is in a low Earth orbit and it has to pass through the South Atlantic anomaly, and this is annoying because it causes hot pixels in the CCDs. Kepler is not bothered by that. So Kuro has a rhythm in its data that's connected with the Earth orbit, and we don't like it, but we have to live with it, okay? So this first result on F stars confirmed what we already knew. This is again an HR diagram with stars of interest for, let's say, planet hunting. But so Kuro, unfortunately, does either seismology or planet hunting. Of course, you want to do both, and that's what Kepler can do to some extent, but it's not designed to do it either. Kepler was designed to find exoplanets and preferably copies of Earth. What this showed us is that the oscillations of F stars, this is what had been predicted from theory. This is what has been measured. So the amplitudes are a bit lower than we had hoped, but it's not a disaster. We can still do the seismology. As you can see here from this frequency spectrum, it's not so easy to compute the large and the small spacing. We can do that, but we do not get to a limit where we can improve the physics as yet. What Kuro did much better, according to me, but I am a bit biased here, is that it gave a discovery of non-radial oscillations in red giant stars. Now, I know that red giants probably are not the most interesting ones for planet hunters, so what did the Kuro people try to do in the exofields? Get rid of the giants before launch, because we don't want them. They disturb our planet detection. Luckily, they did a bad job. Yeah, and we have lots of red giant pulsators because it opened up the entire red part of the HI diagram for seismic studies. And this was the first discovery. So all these stars are in the exoplanet channel. They were not supposed to be observed because they were supposed to be main sequence stars, and they were not supposed to be variable. They have beautiful oscillations. Yeah. And as you see, they scale according to the size of the star. Yeah. Very beautifully proven. It also showed that red giant stars have non-radial modes. Here is an Echelle diagram. How does that work? You have your large spacing, you cut your periodogram into these intervals, and you stack them. And that's what we call an Echelle diagram, okay? And then you can see the types of modes, because as you have seen, the large spacing is between different L values, okay? So here is a star where we have radial modes, dipole mode, quadrupole mode. Yeah. And then we can do the seismology, just as for the sun. Here you see a blow-up of several cases. And this has really given a boost to red giant seismology, where theoretical work has now shown that the diagrams like this can help us to understand if a star is moving up the red giant or is already in the red clump burning helium. You can see this. Why? Because the core is different. And the burning happens in a shell or in a core, and this gives a signature in the oscillation frequencies, which is why these three stars behave slightly differently. Kepler can do this better. I've understood that I'm allowed to show what's in AstroPH, so here we go. Kepler can do better for red giants than Kuro. It's a better machine. It's very simple, okay? So what you show here is perhaps a complicated plot. This is frequency. This is what is written sequential star numbers. So what has happened in the seismology program that Laurence introduced in CASC, as we call it, we have found pulsating red giants, and we have stacked them all together, their frequency, their power spectra. And you see here a signature of what is typical. This is granulation. This is what CoRoT has shown us, and this is confirmed by Kepler. And here are red giants pulsating. These are the most numerous ones because from an evolutionary time scale, this is what you have in helium burning. And here are stars, red giants on the red giant branch moving up. These are lower luminosity than the frequency of these ones, and Kepler has found them, CoRoT has not. This was an empty hole in our red giant seismology so far. And you see, they have higher frequency than the red clump pulsating red giants. Higher frequency, shorter periods, the stars are a bit smaller. As they move up the red giant branch, they become bigger, okay? And then they start burning helium, and so this can be seen directly in their frequency values. Another result that was just found is that these Kepler red giants fulfill what we call the relation between the large spacing and their maximum peak. This has been derived for solar-like stars on the main sequence. And so the question is, does this translate immediately to a similar relation for red giants? The answer is yes. The mode lifetimes of these stars was also unknown. CoRoT already told us that it can be anything depending on if a star is moving up the red giant branch or already descending and on the horizontal branch. This is confirmed by Kepler, but this time for a much broader range of red giants. So we have clear detections in Kepler of radial modes, dipole modes, quadrupole modes, and even L equal to 3, which is quite remarkable because these stars are faint. We have photometry from space. We do see L equal to 3 modes, and so far this has been found for the Sun very clearly, for Alpha Centauri that I showed, but not yet for other stars in a clear-cut way, let's say. So we have that from Kepler. Now I have to say a little bit about massive stars because that happens to be my pet stars. So I'll try to go over this quickly just to give you an idea that we can do seismology across this whole HR diagram, okay? So for massive stars here, the unknowns, as I said, are the core overshooting. This is a crucial parameter that we do not know and that we need to know to do pre-supernova evolutionary tracks and to improve these. And the internal rotation, because we need to know the mixing near the core, okay? Okay. Where did we stand before CoRoT and thus before Kepler? We had huge initiatives from network campaigns that led to first detections of internal rotation. This star is the second star besides the Sun. And when I say star, I tend to omit the white dwarfs. I have to tell that because sometimes I make these people unhappy. Living stars, okay, for which we were able to prove that it cannot rotate rigidly. And this is a very important conclusion because all the evolutionary models of massive stars until that day assumed rigid rotation in the interior of the star. This caused us a lot of pain. I'm showing this table because this has been quite intensive in terms of observing. Look at this. Here are the 5 stars for which we have an estimate of the overshoot parameter. You can find it here. So this is the amount of the path that the bubbling bells cross into the radiative zone, and that determines how much material is taking part in the nuclear fusion, and that's expressed in pressure scale heights here, so it's a dimensionless number. These are the first results, and these are the results of the rigidity of rotation in the stellar core compared to the envelope by this Doppler shift change of frequency type reasoning. Now, for the first result, I measured 20 years, really. I don't want to repeat that experiment because I'll be retired. So it's very inefficient. Nevertheless, to make the first case, we did it, okay? So we monitored this star for 20 years. Look at this, 4 years high-resolution spectroscopy, 5 months multi-site photometry spectroscopy. These are experiments that work, but it's a burden, okay? So we'd rather not repeat it or go ahead in that way, but move to space. And CoRoT, in contrast to Kepler, I must say, CoRoT has a big emphasis on massive stars in its seismology program. For Kepler, this is not suitable because you can't find planets around these stars, okay? So this has been eliminated from the start. Very unfortunate for us, but anyway. So here are CoRoT data of a B star that is a rapid rotator and that has a circumbinary disk, circumstellar disk, sorry. So 25% of all the B stars have a disk around them, and we don't understand very well how that works. One of the options before CoRoT, there were big fights in the literature about how that came to be. One of the opportunities would be to have a beating of non-radial oscillation modes give rise to outbursts. And CoRoT sees an outburst in real time. That's nice. Let's look at the frequency spectrum of this star. This is a movie. Each time showing, we cut the 5 months data. This is work done in Paris. And you see here a frequency spectrum. All the red bars are detected significant frequencies. These are frequencies that we have expressed here in cycles per day. That's just a bizarre unit that we tend to use for these massive stars. And so what you see, here is, let's go through this again, is this is quiescence. We have 2 main frequencies here. These are pressure modes. And watch them, how they evolve. They are dominant, but then they lose power. And you see up here, gravity modes appearing. So somehow there's an interplay between gravity modes and pressure modes that exchange energy and that cause an outburst. And so CoRoT saw this in real time. So one star settles the issue of a 20-year debate in the literature because you can measure uninterruptedly from space. For this 5 months, Kepler will do much longer, but it has no B stars, unless I can convince the G office that they give me some B stars, okay? So this was an important discovery of a massive star, okay? For the details, you need not bother. Just say that by the time that CoRoT did these measurements, we are organized in such a way that we can do the ground-based high-resolution spectroscopy from 1 site or from 2, perhaps from 3. For this star, it worked out, and we could deduce that its 2 dominant modes that cause this beating and the outburst. They look like this if you put them in a Doppler map, as I shown before. So they are high degree modes. This is something that solar-like oscillation people are unfamiliar with. You cannot detect this in photometry from the ground. You may detect it from space, but it's still very difficult. Why? Because you have a cancellation effect. In photometry, you just have integrated light over the surface that you measure. And if you have an equal number of red and blue parts, then you cancel your signal. So it's very difficult to have high degree modes in your signature if you do photometry. In spectroscopy, you Doppler map this. So this is a very different way of measuring, which is why it has more information. Okay? So where do we stand? Trying to round off. Well, I would really, Kuro is magnificent. It's a precursor. MOST also, it's even a smaller machine. It can only do a limited time base. 5 months for us is short as seismologists. Kepler will soon be ahead, and it can do, I guess, at least nominal 3 years, but you must be hoping for much longer. This is crucial for the seismic interpretation of your planet host stars. Okay. What Kepler can do and Kuro cannot do, and that's why I didn't bring any results yet, is do compact stars. This is a niche that only Kepler can give us. So I'm hoping that this will be done. We have several good candidates in the Kepler program, but not many of them. These are very faint stars. But we want to understand stellar evolution. That's the plot I started off with on this planet discovery around compact pulsators. And several of those are in binaries, in eclipsing binaries, and they can lead us to planets. But before that, we have to understand and model the oscillations. Okay? And then, of course, I want to go up to high mass stars for the supernova reason. Kuro has just found oscillations in O stars. This is a new discovery. It's clear-cut. I don't have them with me. It's embargoed, but they are there. And there is one B supergiant where we also detected oscillations and can connect that with an outburst of material-losing stars. So I'm talking about luminous blue variables now, Wolf-Rayet type stars. Okay. This is, I'm afraid, not possible with Kepler because these stars were carefully avoided and are not visible. And then we need to identify many more modes to get you the ages of your planet host. This is a paper by Jørn Christensen Dalsgaard and collaborators on the star that has been measured with Kepler, Q0, Q1 data, Fourier spectrum. You see the granulation, you see the excess bump of the oscillations. This is quite similar to what I've shown you from Kuro, only in this case it's a star with a planet, so it makes it more interesting in that sense to characterize it. Here is an Echelle diagram where the open symbols are stellar models and the filled symbols are the data from Kepler. So it works quite well, and there is a quite good, remember the 1% I was telling you about for the Sun? We have a good handle on the average density of this star. We have a good estimate of the mass and of the radius. This is important for planet people because, of course, if you have the stellar radius and you have a transit, then you have then you can resolve the character of the planets in a much better way. Age, well, 10%, not too bad, because you can't have an age otherwise. You think you can from stellar evolution models, but you cannot, because there are many unknowns in these models. So in this case, there is a 10% accuracy, not too bad. I really am impressed by that. The largest unknown is this convective overshoot thing. That's annoying. We have to understand that and we have to model it. And we can do it, but we need many more stars like this one, and then we can do a statistical analysis of that. Okay. Oh, this is just a fun star we found, a solar-like oscillator in an eclipsing binary from Kepler. So here you see a completely nice eclipse, yeah? And this star happens to be a red giant, the first one discovered, pulsating red giant in an eclipsing binary from Kepler data. And it allowed us, even for the Q1 has only given us one eclipse, a very neat restriction on the parameters of this star, and we have, of course, hoped that it will be followed up intensively by Kepler. So from the oscillations, you see here the oscillations of the primary. This is the oscillation spectrum. We don't understand this yet. Could be G modes, but we don't know yet. could be granulation. This is a clear signature with a large spacing, and from that I'm using scaling relations that I've just shown you seem to work out. We have the radius, the luminosity, and the mass of the red giant, and then you can use the eclipse information to deduce characteristics of the secondary. This is the secondary eclipse, by the way, where some kind of body goes behind the red giant. And now in the Q2 data that we have just received, we see the other eclipse. So we were right, and we can model it much more carefully in the coming month. So I'm claiming that asteroseismology is entering a golden age. We're already there. It's nice. We have based our theory on ground-based network data. This was an immense, really an immense effort by people in the past, let's say 10 years. For white dwarfs, it was particularly successful. The MOST mission has shown us the way. Kuro is functioning excellently. It is prolonged by CNES, by the Space Agency and the partners, to be operational until 2013 now. And I'm not exaggerating if I'm telling you that this is really revolutionizing our view on observational astroseismology. We have our basic theory. We need to refine it. We need to understand better how dense cores of evolved stars work, how rapid rotation works, how nonlinear coupling, as in that BE star, works. And we have to try and understand how that can lead to mass loss and outbursts. And for that, I'm stressing again that Kepler has unique capabilities here. Because of the long-term monitoring, there is no single other instrument that can deliver us this. And again, compact pulsators are really a Kepler niche, because they are too faint for CoRoT. That's the reason, okay? And there are none known in the CoRoT seismology fields. So we are still doing our ground-based work. We need it. That's the same as for the planet confirmation. To avoid false positives, you need a lot of spectroscopy. We need that to characterize the modes. We need that to do an abundance determination. We need that for the surface rotation, so that we can combine it with the frequencies and go to the interior rotation. But we have a lot of work ahead of us, and I'm stopping this talk with an advertisement. Now is a good time to join us for asteroseismology, and to prevent that it takes you a long time, we wrote a book to get you started. I thank you.
Thank you. We can take some questions. Maybe I could start. With the lower amplitudes, does that imply the sun and other solar-type stars won't live as long as we think they would? In other words, the convective overshoot is much less?
The lower amplitudes mainly mean that we have to tune our theory, but it won't have an effect on their lifetime, because the overshoot is happening in the outer layers and not near the core. So each time we measure overshoot in a star where the core is dominantly convective, that has a huge effect.
Got you. Okay.
But not on solar-like stars.
Right, because the convection's on the surface.
Yeah.
We do this so it'll wind up in the recording.
So something like the sun has oscillations on the period of minutes,
That's
and
right.
Kepler does averaging over minutes. Doesn't that basically eliminate your signal?
Well, as you have seen, the answer is no.
So
Yeah.
how?
But you do average over 1 minute. And so in that sense, CoRoT averages over 32 seconds. It does better. Yeah, and we can clearly see that difference. But, well, Kepler wasn't made to do this work. Kepler was made to find planets. And then later on it was realized that it would be nice to have seismic, information on the stars. So what you have to do, of course, is average your theory over 1 minute. And then you can live with that, and it works. Of course, if you go to, like these compact pulsators, we have periodicities that range from 1 to 10 minutes. If you're at the 1 minute, you can't tune these stars. If you're at the 10 minute, you can live with that. But it's just not ideal, but it can still give us good results.
But presumably it works better with bigger stars because they have lower
yes.
frequencies.
Yes, all these B stars that I want to do, long cadence is fine. Half an hour is fine, because the periodicities are several hours to several days. And so that's the half hour is a perfect cadence. Yeah.
Do you think you'll ever be able to make progress with stars like magnetic stars in determining how the magnetic field varies with depth?
Yes, I'm an optimistic person, so my answer is yes. And in fact, we have just discovered two rapidly oscillating AP stars in the Kepler field. And so these are stars with a very strong magnetic field and very short oscillations of periodicities, again, around 10 minutes. So if we can follow them up, and if for years, and if they have a magnetic cycle, then we can try to start studying the effect of this on the oscillations. The problem with these stars is that we have the oscillation signature, we can do the seismology, but we do not have the magnetic field measurements over a long time. So we now have to do follow-up in polarimetry of these objects, but they are very, very faint for that. That will be very difficult. So we will be ahead with the oscillation signature, but we will be lacking the magnetic field information for these stars. And from the ground, it's the other way around. VLT has done studies, spectroscopic studies of these line profile variations of magnetic stars, where we do see the structure in the outer atmosphere and its effect on the line profile variations, but we simply lack enough information to deduce the oscillation frequencies and their character. So somehow we must, find a good case where we would have all this information. And then we can do that, because as rotation shifts frequencies or splits the frequencies, magnetic field splits the frequencies as well, but in a different way than rotation. So we can unravel that if we have a long enough time series, which for the moment we do not have. But these two stars, even though it's only two, we have placed them on a high priority list to follow them with Kepler.
What's precluding you from putting your O and B stars on the Kepler target list? I know you have targets, so what's the problem?
They are too bright, mainly. And so the ones that I presume could be B stars are faint, and I cannot claim that they are young B stars for the moment. I need to do spectroscopy, because probably they are compact B stars, and that's a different story then.
How bright are your known candidates?
The bright candidates are, 5th, 6th magnitude. And the faint candidates are fine. They are 10th, 11th, but I can't claim they are young OB stars. So I'm struggling on.
What are the prospects for some of these large-scale survey projects like LSST and pan-stars and so on? Are the cadences too sparse for this kind of work, or are they going to be useful?
The cadence is too sparse, basically.
Are there any similar projects planned that are not as sparse and will be useful?
There is one, so what we have been doing is organizing ourselves multi-site campaigns with spectrographs around the globe. But this is not very efficient. This works for these massive stars, but it can only, I don't want to do another 20 years of that, okay? What is being developed, but this is just a project for the moment, is a network called SONG. This is led by Aarhus in Denmark, where also the Kepler's Asteroseismology program is led. And the goal is to have 8 telescopes, identical, with high precision spectrographs around the globe. And that is specifically meant to follow up solar-like oscillations in spectroscopy, because then you have the benefit of the spectroscopy. This project has funding for its prototype telescope, and that will be installed in in Tenerife, operational in 2011, 2012, let's say, but we are seeking collaboration to have more nodes. So this is really specifically for that niche of high precision spectroscopy in seismology from the ground. That's the only project that I'm aware of that is really going to do that science case. But since it's such a narrow science case, it's very expensive for what it is. But it's the only way to make progress from the ground. Unless you would be, what I had to do is go through all these tags to get me my telescope time with 50 to 100 astronomers, and it worked out fairly well. We got usually the time we got, but the weather is then blocking us. So duty cycles remain below 40 to 50%, and that's just a pain because your stars oscillate with periodicities of hours to days, and your rhythm of the astronomers is hours to days. That's just a fact of life that I cannot avoid. So.
Are there stars that you actually, are they very young stars that you can't resolve a core for, that you've been able to see?
Sorry, say that again?
Are there extremely young stars that you can't resolve a core for, i.e. that you can't detect the core because they're so young?
Well, if I look at the O stars that have been monitored by Kuro now, we can derive their age as millions of years only, but we see the core structure. So for that we would have to go to the pre-main sequence phase, and that's something that is very interesting, in fact. Pre-main sequence stars, do they have planets? Maybe already formed. And Kepler can do that for pre-main sequence F stars. It should keep them, but I'm not the one who decides on the targets, because we can see that. We have predictions of oscillations. They should have gravity modes. And these are very interesting. That's the purple one that I showed in the beginning. So that potential is there, but I haven't seen any clear-cut results yet.
The way Casca works so far, you've identified targets and then applied for apertures on Kepler. Mm-hmm. When we release 100,000 stars to the archive in June, mm-hmm. how are you going to attack that archive?
Oh, that's very simple. We are ready with our classification software. We're going to run it through, and in 2 weeks' time we will know the pulsators. But then, I can't put them back in, I have been told. Unless I write a GO proposal. Right?
Right, but you'll get more data in a year's time.
Yeah. We will do that. Or you can do that if you want. Our software is available for whoever wants to do that. We built this tool to understand the Kuro exoplanet stars. So the main goal there was planet hunting, but of course there's an immense byproduct, variability of stars. So for the Hertzsprung-Russell diagram, all the classes, all the ellipses I've shown, and on top of them all the types of binaries, we have, how should I say, artificial intelligence codes that tell you how stars in these ellipses should look like in terms of light curves. And we cross-check with the data, and that works quite well.
So just to confirm that, you're going to make Asteroseismology mining software available to everybody?
Yes, if you want it, I am prepared to give it to you, yes.
To the world?
Yes.
Okay.
It's connected with our publications, and you can even find it on ADS. But I'm afraid you will need some help. Because using that as a black box is it's not as simple as that. But it's available. I can even send you my postdoc who developed it to help.
Great, send postdoc.
We don't want to keep this for ourselves. I mean, that's stupid.
Can you comment on which stars will be most applicable, or I guess the best ones for searching for planets through, like it's a Doppler, of watching the frequencies move back and forth?
You mean in spectroscopy, in the line profile variations?
No, so for Kepler we're going to see lots of pulsation modes and so forth, and the modes are going to die and come away with certain lifetimes.
Yeah.
So which stars are going to be best for doing essentially RVs with pulsations to search for massive planets?
So let me see if I get this right. You want to know what kind of stars can give us asteroseismology and planets at the same time?
No, planet goes around.
Yes.
So there's going to be a Doppler shift
Oh, yeah, yeah. So you mean in a timing method way? Yeah. Well, best stars, that depends. In compact stars, it's easiest. Why? Because their periods are very short. So what you need to do to search for this effect is model the oscillations carefully. And then you can get rid of them. Yeah. But the most interesting domain, I would say, in a statistical sense, are F stars. Because F stars on the main sequence, I'm sure lots of them have planets, they have gravity modes. Gravity modes probably interior, but it's very difficult to unravel that because their beat periods are over a year. This is why I'm saying Kepler can do this and nobody else can do this. So if I were in the Kepler team, that's where I would focus on.
Will the frequencies of the star be stable enough to see the wobble?
I think so. We have, these are called Gamma Doradus stars. We have been monitoring them from the ground for 10 years and we see stable frequencies over that amount of time. So that should be okay. Maybe not all of these stars. And depending on their magnetic activity, it may not be so easy, but for the moment we lack data long enough in time base to actually do this. But this will be solved as Kepler will measure longer.
Thanks, everybody, and thank you very much for a really fascinating talk. Let's give her a hand again.